Good afternoon, everyone. I'm Sridhar Kamath. Today's webinar topic will be the introduction to fatigue analysis using FEC. And here's a brief overview. These are the things which we are going to cover in today's webinar. Why do fatigue analysis, and brief introduction to fatigue just to refresh your memory. And also, why do we need intelligent fatigue analysis software such as FEC? We will discuss. And also, how the accuracy of the fatigue analysis matters, that we will discuss. And I have a couple of case studies, and we will also go through one demo problem. Why do fatigue analysis? Simple answer will be because it's important, and also fatigue failures are expensive. In a typical car industry, prototyping cost will be more than around 40%, and also component failing before the optimum fatigue life can mean more expensive when product launch delays and product recalls, warranty claims, and legal liabilities also becomes a big headache. Fatigue failures are more than just financially expensive. We can see one example here. The 1950s Comet Air disaster due to the fatigue failure resulted in devastating loss of life. And apart from that, even the Comet lost the industry lead to Boeing. It took another 50 years to gain parity with the US in sales of passenger aircraft with the launch of Airbus. So we know that means what happens if you don't do fatigue analysis. We know the reason. Now let's look at what happens if you do the fatigue analysis. So the cost benefits can be significant and competitive advantages can be gained. Here we have a Jaguar Land Rover virtual design validation example here. This virtual design validation project by Jaguar Land Rover used FEC TurboLife to look at the high temperature fatigue problem and also design optimization of exhaust manifold. The project enabled Jaguar Land Rover to identify an alternative and cheaper material. And also FESafe enabled Jaguar Land Rover to create a near optimal, nearly a best design and also a design process. As a direct result of this project, Jaguar Land Rover are now reducing the number of prototype tests they are doing exhaust manifold, and also this is leading to a huge cost benefit to the lab. Therefore, fatigue analysis plays a key role in the right first-time design process, and also it will it is just a fraction of cost and time taken for physical testing or prototype phase. Even optimizing the design to reduce material in typical car industry, even if it is 1%, a study says that nearly $60 million can be saved over a production lifetime of that particular model of a vehicle. we will see a brief introduction to fatigue. Here is my component, which is under loading, not just loading, but it's cyclic loading. Because of this cyclic loading, microstructurally you can see, I mean, you cannot see, of course, there will be microstructural intrusions and extrusions on the surface, which will lead a crack generation, and it is called fatigue failure. This one may lead to crack propagation also. Let us understand the three stages of fatigue failure, that is crack initiation, propagation, and fracture. So you are in a much better position if you if you design your component such that cracks do not initiate itself. You are in somewhat worst shape if you allow the cracks to initiate and don't think they are going to grow. So crack initiation is a design criteria in many industries. For many industries, as well as even crack initiation will define the majority of the fatigue life. Crack propagation and failure will be very quick. Once we have initiated the certain length of crack, a lot of our analysis focuses on prediction of fatigue life on crack initiation. A brief introduction to type of loading in coming in fatigue. As you can see, this is a completely, and it's a reversing type of load. You can see load versus time here, and here is a maximum load amplitude, and this is called one cycle of load, and amplitude becomes a range. That is, this is your stress or load range. Range divided by 2 becomes your amplitude. Similarly, minimum load divided by maximum load becomes your stress ratio or load ratio, R. Here you can see two different type of loading, R is equal to 0 and R is equal to -1. R is equal to 0 is completely tensile type loading, and R is equal to -1 is completely reverse type of loading, where magnitude wise both maximum and minimum are equal. Maximum will be in tensile zone and minimum will be in compressive zone. Now let us consider an example of a endurance curve. If we test a steel specimen and if we test it in air, our damage curve looks something like this, whatever we can see on your screen. And load amplitude you can see here, and life is in the horizontal axis, and you can see that both of them are in a log axis. The reason we plot this number of cycles on log scale is because if we don't do it, it will bunch up together, and you cannot visualize it properly. So because of this, we try to model or we try to plot this SN curve in log scale. And you can see here what it signifies, that you can see here. This is your cycle, typical cycle, and you can see this load amplitude in vertical axis. If you have a loading something of magnitude which is less than 10, there is no damage to your model, and we call this point as endurance limit, and below which is the life becomes infinite. And similarly, it is not true, but still let us consider that for time being, let us consider this particular thesis holds good. And we can also consider that infinite life is 10 power 7 cycles in our case. Let us consider one stress amplitude. Earlier, when we were using the SN type of approach, what we were doing is we were calculating stress amplitude, and corresponding stress amplitude will plot it in y-axis, and we will plot a line, and corresponding line coming in horizontal axis. At this point, we will claim that our life is this many number of cycles. Now what I have done is the stress amplitude is reduced, and you can see the life has been increased. So this is a typical approach we can see in old SN type of curve. FECF mainly, the approach of solving FECF is mainly strain life approach, and we will see this with a demo maybe in the end of the session. Further, what happens if the curve slides above? That is nothing but this is not a completely reversible cycle, and we have more tensile component here than the compressive component. So our life changes and it reduces. So this is nothing but the effect of tensile mean stress, and we do mean stress correction for this purpose to use the same SN curve. Similarly, if we have in your loading, if you have more compressive component, the life increases. This is nothing but effect of compressive mean stress. So life is determined by stress amplitude, or of course strain amplitude in strain life curve approach, and mean stress. So if it is that much simple, why do we need complex fatigue softwares? Here's the answer. Stresses will not be always elastic in nature. This stress life curve or SN curve is designed keeping in mind that the stresses will be elastic and not for plastic stress. Similarly, this SN curve is derived for uniaxial type of loading, whereas most of our application are biaxial in nature. Similarly, the loading may be complex, or even in some cases it will be very complex, and SN curve is not designed to handle this much complexity. This is the reason we need intelligent fatigue softwares, and many companies use advanced finite element analysis to calculate design stresses. But the fatigue analysis is often still done by manually picking the stress points from the spreadsheet. Whatever I showed in my previous cases, that is one of the approach they use. And also many companies use Excel sheets also. And these type of methods and hand calculations are kind of inadequate for many reasons. It may be simple scenario, but it will not give you the intended result, or we can put it in other words, it is not reliable. It is unreliable. With these methods, we interpret too much. Means there are a lot of assumptions coming in place, and we are mainly focusing on wrong section and of a model, and again it is impossible to consider all the conditions and alternatives and variables. So for these many reasons we need intelligent softwares. Let us understand this with this example. This is a drive shaft assembly. This is a case study from Dana Automotive. It supports the case for why you need an intelligent software. On this drive shaft components, the crack did not start from the point of maximum stress. As you can see in the slide, there is a maximum stress, principal stress location is different, and shortest life, fatigue life location is different. And this has been confirmed by testing also. So when it comes to more complex loading, the correlation becomes lesser. And in between the stress plot and life plot, there is a dangerous. It is also dangerous to assume that the high stress points are the ones where even fatigue cracks. This is mainly because we have large number of we have a large number of examples to for this claiming this. We have a large number of examples where cracks did not start from the high stress locations. This is mainly because of FEA stresses and loadings. FEA stresses are one part of the story that is coming in FE analysis, whereas loading consideration and the sequence of loading are not considered when it comes to FE analysis, and that can be considered in FE safe. I have another interesting case. This is from a Hyundai motor company. Here the analysis was based on a suspension arm. The benchmark was to investigate the effect of overload as if the vehicle had hit the bump. There were mainly three scenarios which were investigated. The first being, the first was essentially a constant amplitude, but low magnitude. So the load was not changing over time. It is a constant amplitude loading. And FECF predicted the fatigue location at the top of the bolt. You can see it here. And this is where the part failed also. You can see there is a good correlation between testing and FECF. And the second scenario is the loading is scaled up, and load amplitude becomes more again, and you can see the failure. The failure has shifted. Similarly, third case is a combination of first two scenarios. There is a overload followed by a constant amplitude load. Based on first two results, it would seem logical to predict the same failure location. Whereas this is not the case. The failure location is identified by FESAFE shifted significantly. You can see it here. And upon the using these loading, you can see that there is a drastic change in location of life prediction location. And you can see that it has been validated by testing also. I have another case. In this case study, it is from Ford. There is a fatigue assessment study of a oil pan done, which is done taking into account the forming process in the manufacturing. The FECF results on the left, you can see there, excluded the residual stresses caused by the stamping process, whereas the right hand side, it is with including stamping process. So taking the manufacturing effect into account, not only it identified new fatigue spots, but also it has reduced the fatigue life drastically. Initially, the life was nearly 15 years, and it came down to 6 months. This is the effect of manufacturing, effect of considering these manufacturing effect in the fatigue analysis. So these are the things which you cannot consider in your traditional fatigue analysis scenarios where you consider a SN curve or an Excel sheet. So with these three case studies, we wanted to show you why you need intelligent fatigue analysis software and why you need to do fatigue analysis. And we have seen FES stresses are only one part of the story, whereas loading is the other part of the story. And also sequencing and manufacturing effect are very, very important when it comes to fatigue analysis and fatigue life. Moving on, FECF is an intelligent software. It is unique because of the quality of algorithm we use here. Its level of accuracy is only possible because of the advanced fatigue algorithm we use it at the core. So using intelligent fatigue analysis software suite such as FESAFE enables you to do all these things which we listed here. You can take a moment to study these. But in order to do these things effectively, it is essential that firstly and foremost thing is the fatigue analysis software must give you the accurate result, because only accurate results are meaningful, and as we have seen, getting the wrong result are worse than not doing a fatigue analysis itself. This is a typical fatigue analysis process. You can see here, here's where FESAFE fits in. You have a designer who gives the preliminary design, and FE analyst is the one who analyzes it. You can use Abacus, ANSYS, or IDEAS for your FE analysis. and this FE analysis result will be one of your input for FESafe. And FESafe uses FESafe mainly needs three key inputs. One being your result file of FE analysis, second one being your duty cycle, and third is material data. This material data is very, very crucial, whereas as I already told you, our loading is also crucial, and accuracy of this FE analysis result also matters. So FESafe needs all these three key inputs, and when it comes to material database, it is having a nearly 500 material database in its database. You need not search for any fatigue material properties outside your analysis domain. FESafe is having a built-in material database. And also FESafe supports these input for input and output preprocessor as a post processor. These are the supported softwares. FESafe is comprehensive, and you can trust that it will handle any fatigue scenarios. And also all the features you see here are included in a standard version of FESafe. And I think I will leave you to read through these. Few of the new inclusions in FESafe are component of ANSYS Workbench as well as component of Similia EyeSight. And also vibration fatigue is one of the key inclusions which are very crucial in today's fatigue analysis industry. Loading methods in FESafe. Abacus along with FESafe becomes a very good combination for fatigue analysis. Whereas FESafe supports these key loading methods. It can support single load history. It can also support multiple load histories. It can support a sequence of FEA solutions. You can see the example in the right-hand side. Similarly, modal superposition is also one of the loading method in FESafe. This is a PSD fatigue or vibration type of fatigue, wherein PSD curve will be your loading. Multiple load histories in FESafe is one of the key factor of this FESafe. In fact, FESafe is the first commercially available multi-axial fatigue tool. You can see it here. We will see this in the end. I have one case study of that same problem. Moving on to this sequential type of loading, crankshaft and connecting rod analysis. FE analysis we carry out for every 5 degrees, and we have to sequence it to get accurate fatigue analysis. So this sequencing is possible in FESafe, and we can accurately predict fatigue of these type of problems. Another very important case becomes accuracy. Accurate result always allow you firstly the correct fatigue hotspots are very important, and also it allows you to optimize your design for fatigue as well as first time right. This is also very important in today's competitive world. So of course inaccurate results are unreliable, and instead of getting inaccurate results, it is better not to do the analysis. I have couple of case studies where you can see the accuracy of this EFISAFE tool. I have an example here of rotor hub of a pilotless helicopter. This is under huge complex type of loading. These parts are subject to very complex loading from drag and bending and axial type of forces. Yet EFISAFE can take into account these multi-axial stress state as well as still it can accurately predict the fatigue life. So the conclusions mainly from these type of analysis is that conventional uniaxial fatigue methods would simply not able to cope with this type of complexity of loading. And also multi-axial stress in this component and testing the flight is it's nearly impossible. So EFISAFE is the solution, and you can see here the correlation between testing as well as EFISAFE. And from testing, it took nearly 985 hours to generate a crack, whereas EFISAFE predicted the crack generation at 934 hours. Similarly, we have a few more cases of EFISAFE giving a very close result to that of tested result. This is a case study of automotive suspension, wherein generally automotive suspension will be under three different type of loading: braking type of loading, and of course from top the whole vehicle's body will be under this suspension, and because of braking there will be cornering type of load also. So this typically automotive suspension will have three different type of loading. So this is solved very easily in EFISAFE. What we do is we solve FE analysis for unit load analysis, and three unit load linear static analysis we carry out, and we supply that result to EFISAFE. And tested loading cycle. For example, one cycle of loading we will test it and we will supply it to the EFISAFE, and we will do scale and combine operation in EFISAFE. And again, you can see very close correlation between test life and EFISAFE. Here you can see test life is giving 41,000 miles of miles before it generate longer crack. This has already gone to fracture or crack propagation stage, whereas EFISAFE predicted 27,000 mile, and it is crack initiation. So you can see a very close correlation. Again, I have another example of suspension itself, when I can very clearly see the location of this particular crack initiation. You can see right hand side the tested suspension, whereas EFISAFE predicted at the same location you can see the crack initiated. I have another application of a modern design of piston, wherein you can see again it is a quadrisymmetric model, and you can see the correlation of crack initiation locations. So to summarize the things, we understood the basics of EFISAFE and also the need of EFISAFE, and with a couple of case studies we understood how accurate is EFISAFE, and also we further studied a few case studies for correlation type of problem. So finally, what I would like to conclude is EFISAFE is an easy to use tool which gives accurate and reliable results to any engineering fatigue type of problems. I think we will move on to one demo problem. I will launch my EFSAFE. I will select this recent projects where I've done a tube problem. This is a tube problem with a tube with a hole. I have the ODB file available with me where I've already done the FE analysis. First thing, immediately after opening any EFSAFE window, what we do is we clear all the settings, because whatever operation we have done in the previous project, it will always be available in EFSAFE GUI. So it is always better to clear all the settings. This is a problem which we are going to do. This is a tube, notched tube example. This particular tube will be under tensile type of load, as well as the bending type of load, and also torsional type of load. Totally, we have done this problem using 4 steps that I will explain you in detail with the demo. When you launch EFSAFE, you can see these are the 5 windows which you can see here. First window is message log window. Here all the information related to your model and all you can see. If there's any errors or warnings when you upload your model, you can see that. It is just a regular message log. This is your current FE model window where you select your result file. This is one of the key input of EFSAFE. This is your material database window where you have a good amount of material database, and you can filter out the material which you require also. Large amount of materials are available in this material database. Thirdly, loaded data file. So if you have a tested loading signal, you need to import that loading signal here. So the 3 key inputs to EFSAFE, which I explained during my presentation, are all here. FE model or FE result model, fatigue material properties, and also loading file. This is your fatigue from FEA window, wherein you connect these 3 key inputs with your model. All the model information will be available here. Here you will connect your model with the material database. Similarly, loading settings is available where you connect your model with the loading. EFSAFE is also having a few other options like factor of safety or probability calculation, and the gauge fatigue options. And also here we have export option wherein you have the right or you can choose your own output. You can choose damage if you require, and damage per block is also available. So here you can select whatever input or output from fatigue analysis you want, that you can select it here. Now let us do this particular problem. I'll clear this tools, clear data and settings. To current model, I'll come here and I'll give a right. I will click on Open Finite Element Model. Here you'll open your ODB file. It will ask for a pre-scan. Pre-scanning is nothing but the information, whatever available in the ODB, it will scan it and it will give at your disposal. You can select whatever inputs you need to import that you can select. For example, these are the things which are available in my ODB file. This ODB file is having incremental loading is applied and increment wise stresses are also available. I will click only on stresses, and also I want the only at the end of the step. So I'll click on this and I'll give apply to dataset and I'll give OK. So FSF will prompt for units. Whatever unit you have given in your FE model, same unit need to be given here. I've given megapascal here, strain, degree, Newton, and mm. I'll click on this. Okay. It is asking me to edit any group. I'll give yes. By default, your FE analysis tool will create a lot of elemental or nodal groups, which may not be required. For example, here you can see here worn element distorted group is there. Similarly, you have M1 and section. These are all unnecessary groups. What I want is only part. I will move these things here. I'll keep only part. So you can see in current FE model window, we have 4 steps. Step 1 is 80 kilonewton tensile type of loading. Step 2 is 0.9 meganewton mm bending. Similarly, next step is 2.7 meganewton mm bending. And fourth step is 1.35 meganewton millimeter torsion. So what I'll do is I do not have any loaded data file for timing. So what I'll do is I'll create my own loading. I will for demo purpose I will only consider this data set 1, that is nothing but tensile type of loading. I'll go back to loading settings. I'll clear all the loading which is already available. Click on data set. I'll add a user defined load dataset. I'll click on this. It will prompt for me to get a block, load block. I'll give OK. So I can give my own loading here. I will give 010 type of loading here. That is completely tensile type of loading. I'll give OK. So you can see dataset 1, that is nothing but tensile type of loading is cycled from 0 to 1, then again it will go back to 0. Means 0 maximum tensile, 0 maximum tensile, like that it will go. So I have defined one cycle here. How many such cycle before failure should be predicted by FSAFE? Apart from that, FSAF also have few more options which is available here. For example, subgroup option is available, wherein you can select surface or whole group. We have seen from the presentation that fatigue generally starts at the surface. So even you can click on surface group. Whole group option is also available, wherein you can create the whole group. Surface group should be selected where you have a limited time and you want to get your results very quickly. So surface group will be created, selected, and only for the surface fatigue analysis will be done. If you have enough time and if you are if you don't have any hurry, you are not in a hurry, you can select whole group and you can analyze the fatigue. Similarly, you have surface finish factors available here. You can, if you have KT value, you can directly input the KT value, or else you have surface finish values available here. For example, mirror polished surface, you need to select this. Similarly, you have various other options like fine machined, precision forging, that type of surface finishes. Using analysis settings, I generally select my material property. I connect my model with my material property. So here is my material property. I will select, say, Manton 950C grade steel. I'll click on this 950C Manton and I'll give a double click here. So for my part 1.1, it will be selected. Similarly, if all the parts are having the same material, I can double click on material and I can give yes. For all the parts, material 950C Manton is selected. This particular default is a general purpose group, wherein let us say you have some 10 different material groups. You don't want to analyze these things. So if you give do not analyze, it will go and sit in default group. Algorithm. I was talking about algorithm during my presentation. FSAF is having number of complex algorithms available for fatigue life prediction. To make your life easy, what FSAF has done is, there is a default material algorithm available. If you select a particular type of material, even algorithm will be selected by default. For example, for 950C Manton steel, this Brown-Miller-Morrow type of algorithm is selected. Whereas here Brown-Miller is a solution algorithm and Morrow is mean stress correction. And for almost all the steel, ductile type of steel, we use the Brown-Miller algorithm. So if you are a fatigue expert and if you want to change your algorithm, or if you want to overwrite your algorithm, here is the option. By default, it will be material default. You can click on select algorithm to be used. Click here and you can use your own algorithm. For example, biaxial strain life principal strain algorithm you can use with the Morrow mean stress correction, or Walker mean stress correction, or Smith-Watson Topper mean stress correction. Similarly, biaxial stress life approach is available. Uniaxial methods are also available, and a few advanced fatigue algorithms are available. These are mainly for thermal type of applications. Generally, it is always recommended to go ahead with the material default, since already a lot of research has gone into this. Apart from this, there are a couple of other options available here. For example, in-plane residual stress. If you have a in-plane residual stress on your surface, you can double click here and you can give this surface stress. Similarly, if you are going for SN type of approach or SN approach, if you are doing analysis, you have the option to scale your SN curve. You can scale up or scale down using this option. So I have already connected my model with the loading as well as material. As you can see here, I will give analyze. It is asking for overwrite because I've already done one analysis earlier. I will give overwrite. So in the backend, FSF is calculating the fatigue life. You can see the message log for further information. You can see that there is no damage here. So there is no damage. Now what I will do is I will increase my loading magnitude. Instead of 1, I will give 2. We have seen that shift in the tensile type of loading will yield lesser life. So increasing the stress magnitude should give me a life which is less than infinite. It is asking for overwrite.
Muted.
You can see worst life repeats of this many number of cycles. I should tell you that EFISAFE is not having its own pre-processing or post-processing GUI. You have to supply a result file, and your fatigue result file will be written in the same format. For example, you can see it here. I have taken tube underscore 614 .odb. This is in ODB format. Even my output file will always be in ODB format. If you import your source file in RST or any other file format, even your output will always be in the same format. Now I'll open my ODB file using this button, open result folder. Okay, it's already open. I'm opening my fatigue results in Abacus GUI. This is my fatigue life. You can see that In this location, I have life. So this is around 5.23. So this is nothing but 10 to the power 5.23, which will give my fatigue life. And this is your crack initiation. So with this, I would like to conclude my webinar session, and we are open for question and answer session. Those who have a question, they can type in your GoToMeeting sessions.